provide our staff and students with further opportunities to come face to face to learn from and to ask questions of some of the world's most distinguished scientists and internationally renowned authorities in the field of economics and international law. The Nobel Prize was established more than 100 years ago in the view of Alfred Nobel for the encouragement of persons who work for the interest of humanity. We are especially honored to have one such person with us today. Our first Nobel Prize laureate lecturer, Professor Claude Cohen-Tannoudji, who was joint recipient of the Nobel Prize in Physics in 1997 for his momentous achievements in the development of new methods to cool and trap photons with laser light. Without doubt, Professor Cohen-Tannoudji work and his lecture today will serve as an inspiration to us all. I would like to take this opportunity to express our gratitude and appreciation to the International Peace Foundation and Thai Airways International. Without whose generous financial support today, lecture would be not possible. Also, I'd like to thank the Dean and his colleagues in the Faculty of Science for the time and energy they have contributed to organizing this and hosting this event. Professor Cohen-Tannoudji, our most sincere thanks and appreciation to you for honoring our university with your presence and for so generously agreeing to give the inaugural Nobel Prize laureate lecture in this series. We sincerely hope that the memory of you take with you of our university and our city will hasten the return of your good self and your wife in the not too distant future. Thank you very much.
Chapter, the representative of the International Peace Foundation, to say a few words about this series of lectures.
Good afternoon. As a contribution to the lecture for culture of peace and non-violence, initiated and promoted by the United Nations General Assembly, Thailand has been chosen as the host country for the event series of Bridges Dialogue for the Culture of Peace. Initiated by the International Peace Foundation, a non-political, independent foundation to the accomplishment of the 2021 based in Vienna. Between November 2003 and April 2004, already more than 100 events took place with 10 novel laureates as well as other keynote speeches and artists, including the Reverend Jackson, Professor Masih Haile Ismailigo, Dr. Karan Singh, the Honorable Gareth Evans, the Evaporative, Jakob Lutski, and Jesse Norman, who all came to Thailand without any fee or honorarium to promote the kingdom as a center for dialogue and international understanding. Her Royal Highness Princess Maharajah Sirindon graciously presided over several events which imposed a reached audience of 30,000 participants, including different target groups thanks to a variety of partners ranging from major universities and ministries to the Royal Thai Army, NGO, businesses, media and the diplomatic corps, which hosted the events in cooperation with the International Peace Foundation. After the completion of the first series of events and the 6 months intermission, the second and final series of bridges with additional 150 events will be hosted in Bangkok, Chiang Rai, Kanchanaburi, Hong Kong, and Nakhon Ratchasima between December 2004 and April 2005. For this second and final event series, 18 novel worlds of physics, chemistry, medicine, and economics has confirmed their participation, as well as other keynote speakers, including UN Secretary General Boutros Ghali and former UN Inspector Hans. As peace cannot be achieved instantly, but it is a process which needs time, which has not been organized as a single conference, but as an ongoing series of events in which novel warriors and international decision makers build bridges with ideas in all parts of society and with the general public. Many of these novel warriors and keynote speeches have already vowed to come back to Thailand on a regular basis, to build long-term relationships with major Thai institutions and with the Thai nation itself. I thank President Dr. Pongsak, Scientists and Chiang Mai University, all partners and sponsors for your important contribution and cooperation. I'm especially grateful to Professor Cohen-Tannoudji, who came to Thailand without any honorarium to support the event, and I now look forward to his keynote speech and to his important contribution to the event.
As mentioned earlier, this afternoon's speaker, Professor Cohen-Tannoudji, received the Nobel Prize of Physics in 1997. This was recognition of his outstanding work in the field of atom cooling and trapping with laser light. Let me take a couple of minutes for this lecture to give a brief introduction to his CV, and so let everybody know who he is. Professor Prof. Cohen-Tannoudji is a professor at the College de France in Paris, and he does his research at the Laboratory of Physics of the Eco-Normal period in Paris. He was awarded the 1997 Nobel Prize for Physics, joining with Professor Stephen Chu and Dr. William Dinkin for the development of methods to cool and trap atoms with laser light. Born in Contentine, he made his high school study in origin, which was then a French city. He left for Paris in 1953 to attend the Eco-Normal period. In his first year, he studied mathematics, but then came to physics, fascinated by lectures of quantization, Professor Kastler. He continued his study until 1952, when he earned a PhD degree in physics and accepted a teaching course at the University of Paris. In 1973, he was appointed Professor of Atomic and Molecular Physics at the College de France. There, he developed new methods of laser cooling and trapping atoms with laser light. These methods have contributed greatly to increasing our knowledge of the interplay between radiation and matter. They have allowed scientists to study atoms and molecules in gases at a much more detailed level, have opened the way to a deeper understanding of the quantum physical behavior of gases. This may lead to applications such as more precise atomic clocks and atom lasers, which may be used in space navigation and in the developing field of quantum information. Professor Cohen-Tannoudji's lecture today is entitled Manipulating Atom with Light. Please give a warm welcome to Professor Cohen-Tannoudji.
Thank you very much for the introduction. Mr. President, Mr. Vice President, dear colleagues, ladies and gentlemen. Before starting, let me tell you how much I'm happy to be here in Taiwan. This is my first visit to this beautiful country. And I would like to express my deep thanks to the International Peace Foundation for inviting me to spend these few days in Thailand. And I'm very happy to start this lecture in this beautiful university called Chiang. So, my lecture today will be with switch on the light so get more contact. So what I would like to do is to address in a simple way a few general questions, like what is light? And I would like to show you how our idea about light has evolved from considering light as a waves and also as particles called photons. Then how does light interact with atoms? And I would like to introduce a few things about quantum mechanics and about the emission and absorption of photons by atoms. And I would like to ask the following question: is it possible to use and to master this interaction? And I would like then to show that by observing the light which is emitted or absorbed by atoms, we can get a lot of information from atoms. But also, there's something new now, we can use light to act on atoms, to change their velocity, to polarize them, and to manipulate them. So light can be also considered as a tool for acting on atoms, and I would like to give two examples: optical copying and laser cooling. And finally, I would like also to say a few words about the new perspectives, the new research fields which are opened by these new techniques. So let me start with light waves. We know, of course, from about 2 centuries, that light is formed by waves. It's electric and magnetic field oscillating in time and propagating in space with a very high velocity of 300 kilometers per second. And this wave is oscillating with a frequency mu, which can range from the radio wave to the X-ray. Also, at a given time, light is a sinusoidal perturbation with a special period, which is called the wavelength of light. And the color of light is related to the wavelength. And all wave phenomena, light gives rise to interference and diffraction effects, which can be, for example, easily understood in the following way. Suppose that you have a light source, S, and you have a screen with 2 slits, and an observation screen here, and you look at the intensity of the light on the screen here. And to go from S to M, the light can follow 2 paths, SEM or FEM. And depending on the position of M on the screen, these 2 waves will be in phase, in which case the wave amplitude will be doubled, or out of phase, in which case they will cancel out by destructive interference. So the light observed, intensity of the light observed on the screen is expected to exhibit sinusoidal variation, which are called fringes, interference fringes. Okay, so that was the picture of light until the beginning of this century. And a few experiments at the beginning of this century, the last century, showed that light is also a beam of particles called photons. And these particles have an energy E and a linear momentum P given by the so-called Planck-Einstein relation, which are the following relations. The photons associated with the light wave with frequency nu have an energy E equal to h nu, and the linear momentum P given by h2 over T, where h is the basic constant of physics, the so-called Planck constant, which was introduced by Planck in the beginning of the last century, 1900. And the important point is that You cannot consider light only as a wave or only as photon. Light is at the same time like a wave and an ensemble of particles. This is what is called wave-particle duality, and that's a very common concept of modern physics. And let me now consider atoms, the other partner, because I will discuss interaction between atoms and light. Atoms, you know, of course, that atoms consist of electrons, which are light particles, orbiting around a nucleus with a negative charge, much heavier, and with a positive charge. And that's what the so-called planetary model. But if you take classical physics, and if you have a charged particle making an orbit like that, it is accelerated and it radiates energy in space. So the motion of the particle is damped. So you predict at first sight that atoms will be unstable because the electron will fall on the nucleus. And also, since the frequency of the motion changes in time, the frequency of the light emitted should be continuous. So these two conclusions are consequences of classical physics. But they are contradictory with what we observe. We observe, of course, that atoms are stable. We are here. They do not collapse. And the light emitted by an atom has a series of discrete frequencies. The emitted spectrum consists of discrete light. And that forced physicists to introduce quantum mechanics. In fact, the starting point was done by Louis de Brossel, a French physicist, who in 1924 introduced the evolutionary idea that also wave-particle duality applies to matter. More precisely, with every matter particle with mass m and velocity v is associated a wave which is called the Brossel wave, with the wavelength lambda de Brossel given by h, the Planck constant, divided by m, the mass of the atom, times v, the velocity of the particle. More generally, a few years after, Schrödinger showed that the more general state of a matter particle is described by the wave function obeying the so-called Schrödinger equation, which is a basic equation of physics, which explains a lot of different phenomena. And the important point that when you try to solve Schrödinger equation, you find that only certain solutions are physically acceptable. You know, exactly as when you study a music instrument, the string of the violin or the string of the piano, this string can oscillate only at a certain frequency, which are the resonant frequency of the string or of the sonar wave. So that idea is that because you have waves associated with particles, you have also quantization of physical quantity. And the most important quantification is the quantification of the energy that shows that the only possible oscillation frequency of the wave function of an electron around the nucleus corresponds to well-defined energy, which means that the energy of an atom can only take discrete value. And if you draw a horizontal line like that, with an altitude proportional to the energy, you find that the energy of the atom can only have six values, the lowest one, which is called the ground state, then this one, the first excited state, then this one, the second excited state, and so on. So you have a set of discrete energies. And this set of states is what is called the spectrum of energy levels. Now we have this idea of energy levels and can now introduce the basic interaction processes between atoms and photons. And these basic processes are emission processes where an atom goes from an upper state to a lower state by emitting a photon with energy hν. And the reverse process also exists where the atom goes from the lower state to the excited to the upper state by absorbing a photon hν. And you have a very important relation between hν and the difference between the energy EB and EA of the two levels. EB minus EA is equal to hν. And this is nothing but the conservation of energy. Because when the atoms go from B to A, it loses an energy, which is EB minus EA, and this energy is carried away by the photon, which is the reverse state, by the photon. Looking at this equation, you immediately understand that by looking at the frequencies of the light which are emitted by an atom, you can reconstruct the energy levels. And in fact, it turned out that the spectrum of emitted light is not the same for different atoms. The spectrum of light for hydrogen is not the same as for sodium, for rubidium. If you want a spectrum of light is some sort of fingerprint of an atom. So by measuring the frequency, you can know what is the atom which is emitting light. And that's the principle of spectroscopy. And that shows you that by observing the light which is emitted by a medium, you know what are the atoms in this medium, so you get information on the world around us. And for example, this is the way we get information about the composition of the stars, of the planets, of the interstellar space. All information we have on the surrounding world come from the observation of the light which is emitted by the atom in this world. But what I would like to show you before going there, let me also introduce another idea. When an atom is in a Doppler state, I told you that it can go down to a lower state by emission. But in fact, there are two types of emission, and that was introduced by Albert Einstein in 1917 and was very important. There is first what is called spontaneous emission, an isolated atom in the upper state P, inside the state P, falls down to a lower state G after a certain time, which is called the lifetime of the excited state, the radiative lifetime. And it can do that even if the atom is alone. It spontaneously emits the photon. And the radiative lifetime, the order of magnitude is about 10 nanoseconds, 10 minus 8 seconds. And spontaneous emission can be occurred in any direction. It can emit the photon in any possible direction. But to interpret the black body radiation, Einstein was led to the idea that there was another type of emission which is called induced emission, and which is the following one. If you have an atom in the upper state, E, and if the photon, H nu, with a good frequency, is impinging on the atom, the atom to go to the ground state, G, by emitting the photon, which is exactly the twin of the photon which is inducing this emission. It has the same energy, the same frequency, the same polarization, the same direction. So that's called induced emission because this emission is induced by incoming light. When it was discovered, this process was considered as purely academic. But a few decades after that, after 1917, in the end of the 1940s, physicists were using this new type of emission to make something very exciting and very interesting. To explain that, let me first explain what is thermal equilibrium. When you have a medium in thermal equilibrium, you can show that if you have many atoms in thermal equilibrium, you can show that if you have two levels, E1 and E2, the lower level is more populated than the upper level. That's the Boltzmann law. Okay, but physicists started by collision process, by excitation with light, to produce non-equilibrium situation where the upper level, E2, can be more populated than the lower level. A medium like that is called an inverted medium. Inverted because the excited state is more populated than the lower state. It's not an equilibrium. And then Cohen-Tannoudji had a very bright idea that if you send light on an inverted medium like that, if light with the good frequency passes through a medium, which is inverted, the new photons, which appears by induced emission, and the number of which is proportional to the population of this state, is larger than the number of photons which disappear because of absorption. So you have more new photons appearing than photons disappearing. That means that the light is amplified. Okay? So, because of induced emission, a light beam, a resonant light beam passing through an inverted medium can be amplified. And if you put such an amplifying medium between two mirrors like that, you see that the light rays can be reflected back and forth between the two mirrors and pass through the medium several times. So it can undergo several implications. And if the loss due to the fact that the mirrors are not perfect is smaller the gain due to the amplifying medium, the amplifier becomes an oscillator. As in electronics, when you have an amplifier which has a gain larger than the loss, it becomes an oscillator. And this oscillator, this is what is called the laser. Laser is an acronym for light amplification by stimulated emission radiation. And the laser appeared in the beginning of the 1960s, and we have now at our disposal in the laboratory new sources like this one with incredibly interesting properties of directivity, coherence, brightness, and that has introduced a lot of new possibilities for basic research and also a lot of application, for the treatment of the retina with laser light, for the CD record, the telemetry with laser, the cutting of material with laser light, also for the telecommunication by optical fiber and so on. That's a very beautiful example how the basic research initiated by Einstein and 30 years after, taken again by Charlie Brown, can open the way to a lot of new physics and new applications. Now, what I would like to show that will be the main part of my lecture, that light is not only a source of information on atoms, but it is also a tool for acting on atoms. And why? It's because by using resonant or quasi-resonant interaction between light and atoms, photon atoms, we can control the various degrees of freedom of an atom. We can control the angular momentum, the position, and the velocity. You can in fact use resonant exchanges of energy, linear momentum, angular momentum between atoms and photons for getting new types of atoms, new properties of atoms. In fact, you use the basic conservation laws of physics for manipulating atoms. And I would like to give you two examples. First example is the transfer of angular momentum from light to atoms. And let me first remind you or introduce you what is atomic angular momentum. Atoms can be considered as spinning tops. They are rotating around themselves, and they have what is called an angular momentum, like a top. And as all physical quantities, this angular momentum is quantized. If you consider the projection of the angular momentum on the z-axis, this projection, for example, in the central case of what is called spin 1/2 atom, can take only two values. This one spin up, or this one spin down. You cannot have the angular only spin up and spin down. Quantization of angular momentum. Of course, if you have a rotating charge, you have also magnetic moment. So an atom can have magnetic moment up or magnetic moment down. Now, if you put a static magnetic field, this magnetic moment and this magnetic moment will have different energy. So you will get two energy levels corresponding to the two particular orientation of the spin, separate by a splitting here, which is proportional to the magnetic field. You have a splitting which can be written as delta E equals H, the Planck constant, times the frequency uZ, which is the Zeeman frequency, and which is proportional to the magnetic field B. And of course, magnetic resonance, which is very important phenomenon in physics. Absorption and emission of photon between these two states, which fall in the radio frequency domain, this is what is called magnetic resonance. By applying the radio frequency field with a good frequency, uZ, you can flip the spin and transform the spin from spin up to spin down, and vice versa. That is called magnetic resonance. But now, if you work at room temperature and in ordinary magnetic field, like the Earth's magnetic field, the Boltzmann factor means that the two spin states, spin up and spin down, are nearly equal population. There's a little more spin like that than spin like that, but they are nearly equal. So the polarization is very weak. That means that the magnetic resonance signals, which are proportional to the difference of population between the two states, because you must have more condition in one way than the other way, can be observed usually only in dense systems, like liquids or solids, because there are many spins. Even if you have a low polarization, there are many spins, you can detect magnetic resonance. It's very difficult to detect magnetic resonance in gases, in gaseous structures. And then there was a very clever idea of my thesis supervisor, Kastler, and his colleague Brossel, the following one. The following idea is that photons, if they are polarized, if the light is polarized, photons have also an angular momentum. And it's much easier to polarize light. You just take a light beam and you put a polarizer. So it's easier to get polarized photons. Photons have an angular momentum. And when atoms absorb these photons, they gain the momentum, angular momentum of the photons which are absorbed. So by exciting atoms with polarized light, atoms can get the angular momentum of the photon and become polarized. And you can get in this way high degree of polarization, 90%. And you can easily observe magnetic resonance in gaseous cycles. And that was a method which was very powerful, very lot of application, and that because of that Kastler got the Nobel Prize in 1966 for the discovery of optical pumping. Of course, I have no time to describe all applications of optical pumping. I would like to give you one, which was completely unexpected. And the idea is the following. About 10 years ago, some people had the idea of polarizing helium-3 atoms by optical pumping. You know, helium is the hard gas, it does not have for it. So you can have helium, you mix helium polarized by optical pumping with air, and you have a patient breathing this mixture and filling the lungs with polarized gas. And the degree of polarization is high enough so that you can make a magnetic resonance image of the cavity of the lung. Usually, MRI, magnetic resonance imaging, detect the protons of the hydrogen atoms of the water molecules. So MRI detects only the liquid or solid part of the body. You detect the bone, the flesh, the blood, but you don't detect the vacuum or the empty part of the blood. So by using this technique, you can now see the vacuum part. And in the next slide, I'll show you two MRI pictures. On the left, it's a proton MRI, so where you detect only the water molecule, you detect the cause, the stomach, the esophagus, the lungs here, but you don't detect the lung. And in the right part, you have the helium-3 MRI, and then you detect the empty part, the cavity of the lung, and that becomes a very powerful technique of lung disease. And no politician would have planned such a discovery. You know, the politicians like to make programs. They want to solve this problem at this time, this time, this time. I don't think this is the way that research is making progress. Research, the most important application, the result of this MRI come in an unexpected way as a result of basic research. And nobody would have planned this discovery that became as a consequence of a big step in basic research. So, second application, how you can manipulate the depth of the matter, let me introduce the idea of light shift, because it will be useful for the following part. In fact, that was my thesis work in 1962. You can show by theoretical experiment that if you excite an atom with light which is slightly detuned from resonance, the levels are shifted by light. For example, let me show here. If you excite the two-level atom with non-resonant light, with a frequency omega light larger than omega A atomic frequency, if the light is decreased to the blue, ground state is shifted by the amount delta Eg. If you like, it's equal to the red, omega is smaller than omega A. Shift is negative. So you have a shift of the ground state proportional to the right and having the same sign as with the Joule. So you can manipulate the energy of the ground state by a light beam and by changing the frequency of the light beam. Okay, can we now take a third example and discuss the exchange of angular momentum between atoms and photons, the exchange of energy, of course. Let me now consider the exchange of linear momentum. And let me show you how you can get in this way huge force acting on atoms. And that is very simple to explain, and it's due to the recoil of an atom absorbing or emitting the photon. I'm sure that you have all seen the tennis racket hit by a ball. When the ball hits the racket recoils. Or when a gun emits a bullet, the gun recoils. That's conservation of linear momentum. If you have an atom in the ground state, G at rest, and if it is excited by a photon which is resonant, and we share the linear momentum H over C, when the atom absorbs the photon, it goes to the upper state, and the total momentum is conserved. The photon has disappeared, the momentum of the initial state is H over C, so the atom must recoil with the linear momentum mv recoil equals H over C. That means that when the atom absorbs the photon, it recoils with the velocity v recoil equals H over mc. So the atom recoils at rest, after absorbing the photon, is moving. When it is in the excited state, I remember what I told you, in the excited state, it does not remain forever. After a certain time, it falls down to the ground state by photon emission. After a time tau r, which is the order of 10 nanoseconds, and it emits a photon in all possible directions. And the probabilities of photon emission are such that the probability of emitting a photon to this direction in the opposite one are equal. So on the average, if you go either in this way or this way, so on the average, the momentum loss due to emission is equal to 0. Now, in what is called the Fluorescent cycle, the cycle formed by the absorption followed by photon emission, the velocity change delta V of the atom is only due on the average to the absorption process. And it is given by delta V equals V equals H over mc. And when you put the number here, you find that in the optical domain, the recoil velocity, the velocity change per cycle is on the order 10 to minus 2 meters per second, 1 centimeter per second. It's very small, it's very qualified. But if the atom is in a laser beam, resonant laser beam, after the cycle, the atom in the cluster, it can absorb the second photon, the third photon, and so on. It can undergo several cycles. And how many cycles per second W can it make? Let me call W is number. And since the duration of the cycle is determined by the lifetime of the excited state, roughly speaking, the number of cycles is 1 over tau r. And since tau r is on the order of 10 minus 8 seconds, the number of cycles is 10 to the 8, 100 million. So an atom in the gravity can make 100 million cycles per second. So what is the velocity change per second? What is the mean velocity change per second? In physics, the velocity change per second is what is called the acceleration or the deceleration. And the velocity change per second is equal to the velocity change delta V per cycle times the number of cycles per second. The velocity change per cycle is very small. The number of cycles per second is 1 over tau r, and it is 10 minus 2, 10 to the 8. When you multiply 10 minus 2 by 10 to the 8, you get 10 to the 6 meters per second squared. So the acceleration or deceleration of an atom in resonance gravity can be 10 to the 6 meters per second squared. That is to say 10 to the 5 the acceleration due to gravity, 10 to the 5 g. You know, like when a cosmonaut undergoes 2 or 3 g, it's very hard to become here. And the 1,000 times bigger. So that means that the matter in the resonance of the beam experiences a huge force, which is called magnetic pressure force. And you can now use this force to manipulate the velocity to slow down and to cool atoms. Let me first explain to you how it is going to slow down. Slow down means reducing the mean velocity. You reduce the mean velocity to 1 kilometer. But in physics, the temperature is related not to the mean velocity, but to the velocity spread around the mean value. And if you are able to reduce the velocity spread, you cool the atoms. And in fact, many methods have been devised, invented for cooling atoms and for slowing down. And before explaining them, let me just tell you that with this method, you can achieve temperature on the order 10 minus 6 degree Kelvin, 1 microkelvin. And you can reduce the velocity spread to value on the order of 1 centimeter per second, even less. And to compare with what exists in this room, temperature is 300 Kelvin. So it's 300 million times bigger rather than the temperature we are able to achieve by electron cooling. And at room temperature, the molecules of the air are traveling with velocities which are 1 kilometer per second. So you go from 1 kilometer per second to 1 centimeter per second. You see a dramatic reduction of the velocity of the atom. So let me first explain to you how to stop an atomic beam. You have an atomic beam coming from an organ, with a velocity which is typically a kilometer per second, 10 to the 3 meters per second. And you irradiate this atomic beam with a counter-propagating laser beam with a frequency which is at resonance. And you see that the deceleration will be 10 to the 6 meters per second square. If you start with 10 to the 3 meters per second, you will stop the atom in 10 to the 3 divided by 10 to the 6 in 1 millisecond. In 1 millisecond, the atom are stopped. And the travel over a distance L, which is given by a high school formula, V0 squared divided by 2A, V0 squared is 10 to the 6, A 10 to the 6, so we get 4.5 meters. That means in a laboratory experiment, in a distance of the order of 1 meter, you can stop an atomic beam. And of course, if you look at this experiment, you have immediately an objection. When the atoms start to be slowed down, the velocity changes. And because of the Doppler effect, if they were at resonance at the beginning, after a short time, they will be out of resonance with the laser beam, and the force will decrease. But my colleague, William Phillips, who got the Nobel Prize to send me, they have a very ingenious idea, is to put around the atomic beam a solenoid with a number of terms which vary with space. And it turned out that the magnetic field shifts the atomic level, that is called the Taylor effect. And the profile of the atomic beam, the magnetic field, is calculated in such a way that the change of the atomic frequency at the atom travel here compensates exactly the change of the resonance frequency due to the Doppler effect. And then you can maintain the resonance condition over the whole trajectory and stop the atom in a distance from the other 1 meter. That's called demand flower. And of course, you can also, let me show you a picture here. You can see on this picture that the end of the solenoid, you can see here, that's red light. And this trajectory here is the light which is emitted by the atom, which comes from the organ from this side, which are stopped here, and which return. They are decelerating and return to the organ. And you see the stop here. And you see the stop eye. You can see by eye, because for sodium, the resonance light is in the yellow sources of the highway. And also, there is another solution with laser diode. You can easily change the frequency of the electronic time. So you can stop an atomic beam. How can you cool it? And I will first introduce the simplest cooling scheme, the so-called Doppler cooling, which was introduced by these people in the middle of 19th century. And in this scheme, instead of using a single laser beam, you use two counter-propagating laser beams. with the same frequency mu-n, the same intensity, and mu-n is slightly detuned to the right. Mu-n is slightly smaller than the atomic frequency. Okay? So what happens? If the atom is at rest, there is no Doppler effect because it is at rest. The two frequencies are the same. Since the two intensities are the same, the two radiation pressure force are the same and opposite, so the total force is equal to 0. The two radiation pressure force cancel out. There is no force. If the atom is moving to the right, like here, because of the Doppler effect, the frequency, the apparent frequency of the beam will be shifted up, and the frequency of the beam will be shifted down. That's the Doppler effect. If this frequency is shifted up, since it was smaller than mu-a, it will get closer to mu-a, so it will be more resonant, more photons will be absorbed, the force will increase. Here, since the frequency is shifted down, it will be still farther from the resonant, less photons will be absorbed, and the force will decrease. So you see that as a consequence of the Doppler effect, the two forces no longer cancel out, and the force which wins the force opposite to the velocity. And if you make the power extension of the force, you find that the force experienced by the atom can be written as minus alpha v, where v is the velocity, alpha a coefficient called friction coefficient. So you have a force which is opposite to the velocity and proportional to v for this ball. It's exactly what you have when you have a pot of honey, the spoon in the pot, and when you try to move the spoon, the faster you go, the bigger the force. It's the viscous medium that viscosity. So you have achieved the viscous medium, and the physicists who observe that call it optical molasses. It's the molasses where the phonate is replaced by light. You have a very viscous medium achieved by light. And for example, that explains in one dimension. If you add another figure of y, a figure of z, you can remove the three components of the velocity, and you see here the molasses of sodium atom at the intersection of 6 beta b. 2 like that, 2 like that, and 2 like that. In fact, when people started to measure the velocity distribution, they found that the temperature which was observed was different from the theory prediction. In fact, because of this, that means you cannot go to zero. You take to the limit, and here again you find Einstein. Einstein did the theory of this effect on your motion paper 100 years ago, 1905. You see that you have a damping due to laser cooling, but because quantization emission is random direction, after each cycle, the atom recalls in the random direction, so you have a random. And exactly at the Brossel motion, you have a competition between laser cooling, which reduces velocity spread, and this random walk, which increases the velocity spread due to momentum diffusion. And you can calculate the steady state and get the equilibrium temperature. And when you make a theory of Doppler cooling, you expect to find that the minimum temperature you can get by this scheme is on the order of a few hundred microkelvin, which is already very nice. But in fact, when people measure this temperature, they found that the temperature was greater. That not usually, when you do experiment, usually you find something working less good than predicted by theory. Here it was bigger. But perhaps before explaining what happened, we can ask me how can you measure the temperature of the molasses? It's a very direct measure because we use the thermometer. So what people do is to show the time of flight technique. They have the molasses here, and with the 6 laser beam. And at a certain time, T0, they switch off the laser beam. So the atoms are free, they start with their initial velocity, and they form some sort of a shower. Each atom makes a parabola, starting from the initial point, with the initial velocity, makes a parabola. And if you put a laser beam, a probe laser beam about a few centimeters below, you can detect the time at which, after switching off the laser beam, the atom pass through detecting deflection of the probe laser beam. And you measure the distribution of time. It is determined by treating the acceleration new to gravity that you know, to initial position distribution of the atom that you can measure by taking the picture of the photograph, and by the initial velocity distribution, which is what you want to measure. So the temperature is related to the velocity distribution. And by fitting the experimental signal to the Maximilian distribution velocity, you can measure the temperature. And this way you find temperature about 100 times lower than expected. So what's happening, and this is what we have identified in Paris with my young colleague Claude, and this is the following thing, which is a nice application of particle pumping and light shift. This is why I introduced it just before. You have in the ground state of atoms, there is a level. It's been done for example until now. When you have two contemporaneous resonances, current beam, they interfere, and you get a standing wave. Intensity and the polarization, which are specially modulated. Now, the light shift of the two levels, plus or minus, are not the same, because they depend on the polarization. And what you find that the energy of T plus and the energy of T minus are specially modulated in different ways. And also because the light is not too far from the resonance, the atom can still absorb light from one level, go to this like we say, and fall in the other level. You can have the pumping between the two levels. And you can achieve a situation like that the energy modulation of T plus, that's the special modulation of T minus, and you are also optical pumping taking you from, for example here, G minus to G plus, or from G plus to G minus. And you achieve a situation where an atom starting from this place, in the bottom of the valley, climbs the potential beam and reach the top of the beam where it has a large probability to be optically pumped to the other state level, that is to the bottom of the valley, and from there it climbs again, put back, climbs again, and you see it's exactly in the situation of the hero of the Greek mythology, Sisyphus, who was condemned by the gods to roll up the stone to the top of the mountain, and when it got to the top, the god was putting him back again at the bottom. He had to do the job again and again. This is what happened here, and that's exhausting. And you can make the theory of this exact and show that explains completely what you observed. And there are no experiments also to explain exactly what happened. And by this technique, we can reach one big population. And we have also developed in place another method which I would like to explain, where you can reach nanolevel, 10 minus 9 Kelvin. Okay, so just to show you, also I explained to you how to reduce the that I have to explain to you how to travel, how to confine them in a small place. And here again we use light shift. And what we do is the following. We take a focus laser beam like that. Focus, and the beam is detuned to the red. Omega F is smaller than omega A. So the intensity is maximum at the focus. And remember that when the light is detuned to the red, the shift of the downstate is negative. So when you cut the laser beam, the shift of the downstate is negative, that's your minimum, and you do it again. And whatever direction, you always find a beam. You get a potential well where atoms can be trapped. If they are slow enough. And that is called the laser trap. It's very efficient. You can trap atoms at the focus of the laser beam, and by moving the laser beam, you can transport atoms where you want. And in fact, that also can be used for biological objects. You can trap with the laser beam biological objects like viruses or bacteria. This is what is called optical tweezers in biology, called optical tweezers. Of course, we have here also other traps. Some of them are being done in our laboratory, which use radiation pressure force and magnetic field by them. Now it's possible to trap and to move atoms. And just to give you an idea how it looks like, let me switch this to another time. Get a bowl, a valve containing about half a liter volume, containing a cesium vapor at room temperature. And at room temperature, you can take the cell, the valve, you can take set by hand. And you have cooling atoms trapping the atom into some center of cell. And this, the orange spot here, is the cloud of about 100 million atoms, which are in the center of the cell at the temperature of 1 micrometer. So you have in the cell, which you can take by hand, and the center of the cell, you have a sample of atoms which are 1 micrometer. That's an example of what you can do with this technique. And a typical experiment is shown here. The table here is about 3 meters by 2 meters. That looks complicated, but that set of lenses, polarizers to guide the laser beam, the cooling laser beam to traffic laser beam. An experiment like that can be managed by 2 people. It's not like high energy where you have 100 people working in an experiment. So if you have a nice idea, you can immediately try it. That is great. So now let me ask, why doing that? And what is the interest of this approach? And that will give you 3 main ideas. First of all, cold atoms move slowly. So in the observation volume, there depends inversion on the time and thermal atoms which move and when we do the consumption. So you can observe slow atoms for inversion on the time. And in physics, there is time energy uncertainty relation, which tells you that the longer you observe the system, the more precise the measurement you can perform on the system. So with cold atoms, you can make ultra high resolution spectroscopy. You can measure atomic frequency with a very high accuracy, and you can use this frequency for making clocks. And you can make ultra precise atomic clocks. Secondly, you remember that the double wavelength is H divided by F V. So the double wavelength is inversely proportional to V. If V is small, the double wavelength is large. So it's much easier to observe the wave nature of atoms on cold atoms. And a lot of new research fields have been done. For example, atomic uniformity. You can repeat with the double wave. All experiments done with optical wave and the work. And also, when atoms are not only cold, but if the density of atoms in the cell is high enough, when the distance between 2 atoms, the mean distance between 2 atoms becomes confined or smaller than the double wavelength, then the wave function of the laser will start to overlap to interfere. And the phenomenon, once again predicted by Einstein in 1924, the so-called Bose-Einstein conversation, can be observed on gases that was achieved in 1995 by three physicists, Eric Cornell, Karl Weinman, and Wolfgang Piccari, because we were right in 2001 for this discovery. So let me explain at least the 2 first applications, because I will have no time to describe the last one. Atomic clocks. First, let me tell you what is a clock. What is a clock? The clock is an oscillation. It's a quartz. Every of you will have a quartz. It's an oscillation. Okay, but if you take a quartz, 2 different quartz have not the same frequency. And even the same quartz, as a function of time, the frequency is not stable. It's rising temperature and so on. So you have to stabilize the frequency of the quartz on a given frequency. And if you stabilize the frequency of the quartz on an atomic line, it's that. And people achieve what they call atomic frontal. They take a ball of 4 atoms, and with the laser pulse, they show the atom like that. And the atom pass once on the way up through the cavity where they measure the frequency, and once on the way up. They form a fountain, like a fountain of water, except that the water molecules, the water drops are acted by atoms. And if you have something like that, you see that the time passing in the observation volume here, the way up and the way down, is about 1.1 seconds. Whereas if you have a beam with 1 kilometer per second traveling over a distance of 1 meter, you have 1 meter. So if you include the observation time by 200 magnitude. And that's why the cesium photon, which have been achieved by my colleague Christophe Salomon in Paris, where you get a curve like that, the so-called Ramsey fingers, give now are the best curve in the world. They have now stability of 1.6 10 to the minus 16 for an international time of scan of about a few hours, and they have an accuracy of 7 10 to the minus 16. To give you an idea of that accuracy, if you take a clock like that, starting at tick of the road, 300 million years after, it will be modeled by network possible. So it gives the accuracy and the stability of the clock. So you can ask, what can we do with clocks? Of course, we can improve dramatically the GPS system, which use atomic clock and satellites. You can improve the synchronization of the information through fiber, but you need very precise time measurement. And you can also make tests of basic physics, of general relativity, by measuring, for example, the ratio of the frequency of the rubidium clock and the cesium clock versus time. You measure intermittency. You can change some cosmological models which predict that the fundamental component of physics should vary in time. And that the basic question which can now be addressed in a laboratory experiment. Of course, if you try to improve this clock still further, you can throw the atom at higher altitude, but then you have to shift the magnetic field higher and higher. That's not easy. So the best thing is to go to microdynamics, to go to space, where you have no gravity. And in Paris, we started a series of experiments, what we call zero-shift planes. We take an Airbus or a Caravelle, like that, and the pilot stops the engine. So the plane is free flight, it makes a parabola. When the plane falls down, the pilot, of course, fortunately, puts the engine back, and you make a second parabola. And in the plane, you have about 20 groups doing experiments, because each parabola lasts about 20 seconds. And during 20 seconds, you have probability to get those experiments. If you are sick for 2 hours. I was not allowed to do that because I was too old, but I learned to do it. Then the next slide shows you here the quadratic groups floating in space going to parabola. Then they could, and the experiment was successful. It showed that it's possible to synchronize the laser beam. You can do experiment in such an environment. And now we have a project to put such that by going to space, you still improve by 1 or 2 orders of magnitude the stability of the clock compared to Earth. And we have now a project to put such a clock in the space station. I don't know when, 2006 or 2007, depending on the budget, because it's an expensive experiment. And you will have of the laser hydrogen laser, the quadratic clock in the station, giving time to all clock in space in Earth, synchronizing all space, all time reference for all space clock, validation of space clock and test of fundamental theory. Because the general theory of relativity predicts that the time in the gravitational field, two different gravitational fields are not shared. So that's an example also of basic application of basic research. And by students, the last example will be the interference between double waves. And remember the experiment I showed at the beginning, the young field interference, now can be repeated with convergence. And there will be an experiment which has been done by 2 Japanese colleagues, they started with the cloud of the morass of million metastable atoms. They dropped, they switch on the beam, so the atom form. They pass through the screen with 2 slits, and we have here the observation plate. And since the atoms are cooled in a highly excited metastable state with a long lifetime of several seconds, when such an atom hits the plate, it gives rise to a lot of electrons, and you can detect them one by one. And this is what you observe. And really, I'm not moving, but I've seen the movie and I've seen the experiment in real time. When you see on the plate, point here, then a point here, point here, point here. At the beginning, it will completely unknown. So each of these points is an atom the impact of a given atom, a single atom. But when you have many, many events, you see that you have places where you have many atoms coming, and places where you have less atoms, and you get free. And to interfere is exactly what you calculate by using the only formula, replacing the wavelength of the light by the one wavelength. And I like very much this experiment, because it clearly exhibits the wave-particle duality for matter. Each atom is a particle, because it gives rise to a localized impact. But each atom is at the same time a wave, because you have a modulation of the probability to get an impact. And the connection between the wave and the particle is probability. The waves give you the possibility to calculate the probability that the particle manifests itself. So now this experiment is used in all quantum mechanics lectures, in all quantum mechanics textbooks, because it's really the earth of quantum mechanics. You cannot see through which hole the atom passes. The wave passes through the two holes. If you want to know the divide and experiment is determining through what slit the atom passes to destroy the interference effect. Show the wave particle duality. Of course, this is an experiment. Now also, interferometers can be built with the wave. And for example, gyrometers using the so-called cycle effect, built by cold atoms using double wave, can detect now rotation speed, which are 10,000 times smaller, lower than the rotation speed of the Earth. The Earth makes 1 turn during 22 hours. You can detect rotation speed, which are 10,000 times smaller. So you have a very sensitive gyrometer, which also given the same image, natural, could be used in plane to measure the rotation speed and navigation. I have no time to describe the last application, which is when the noise, the size of the wave function becomes comparable to the mean distance between atoms. The atom condenses in the lowest energy state in the trap which contains them, and you have a macroscopic number of atoms all in the same quantum state, and that's called Einstein condensation. So I switch immediately to my conclusion, because otherwise it will be too long. I think I give a lecture now, so you can find the slide after. Let me just mention why. Now the field of Bose-Einstein condensation is terribly exciting. There are about 1,000 papers that are accredited every year on this subject. And why? Why it's so important? It's because these matter waves, where you have a million atoms, all with the same wave function in harmonic time, they exhibit macroscopic quantum properties like superfluidity, coherence, which up to now were observed only in balanced systems, like superfluidity of supercomputers. But now you have the same phenomena observed on gaseous samples. And in gaseous samples, the new feature is that these properties, superfluidity for example, appears in systems which are about 100,000 times more dilute than air. Whereas superfluid helium is 100,000 times more dense than air. So you observe this basic quantum macroscopic effect on the very small dilute systems that they call ultra-low, where the interaction between atoms is much weaker. And we can be taken care much more precisely. So you can explain the phenomena and include the effect of interaction in a much cleaner controlled way. You can have a better understanding of this problem. First of all, by varying the magnetic field, you can change the effective interaction between atoms and go continuously from an attractive gas to a perfect gas without interaction to a repulsive gas. So you have a long experiment allowing you to change the interaction at will, as you want. So you have a flexibility in this experiment which has provided a much better understanding of this quantum macroscopic phenomenon. And perhaps before finishing, just so that's a brief introduction, of course, for basic research, and just a list of various applications of optical pumping, data pooling, tracking, magnetometers. with optically formed atoms, MRI of the line with optically formed helium-2 atoms, atomic clocks with couple atoms reaching a relative frequency stability and accuracy of a few 10^16. Atomic lithography, because with the cold atom you can focus them on the substrate and deposit atoms with nanometer size. Atomic interferometer, radiometer, gyrometers with double weight. Atom lasers, for atom lasers, let me first display to you a laser in a cavity. Two mirrors, I showed you before, two mirrors. In two mirrors, you have some cavity modes, which are the equivalent of quantum states for the photon field. You have cavity modes, and one of these modes is macroscopically multiplied by photon. And one of the mirrors is not perfect, and you have a beam of photons coming out from the macroscopically multiplied mode. You can do the same thing with the Brossel condensate. Brossel condensate is the quantum mode, quantum state in a car, which is macroscopically multiplied with atoms. And by making a small hole in the car, you can extract a beam of double wave, which is coherent, and which can be called atom laser. That's an example of an atom laser coming out of the condensate. So you can repeat with double wave what has been done with optical waves. What else? Also a very exciting situation now, a lot of people are working on that, by this increase of our possibility of manipulating atoms. We can use atoms as quantum bits of information. You know, classical bits is a system which has plus or minus 1 or 0. The quantum bit is there was two equivalent atoms, but E.G., but you know what is interesting is that you have not only E.G., but you have all energy mathematician, C1E plus C2G, where C1 and C2 are two units. So the number of states of the quantum bit is much larger than the two states of the classical bit. And people are considering to use the quantum bit to make quantum gates, quantum logic, and hopefully, I don't know where, after 2 or 3 decades, the quantum computer, which will be much more efficient than classical computer. And I'd like to say, as before, that most of these applications were not done in a, were not the result of programs. They were just, almost the most important application comes only from breakthrough. This continues to change in technology, which is due to fundamental discovery. And that's important to keep in mind. A good politician should support basic research. Because the technology which we use in 20 years from now is what we do now in the research about. So I am reaching my conclusion now. I hope to have convinced you that our ability to control and to manipulate quantum systems like atoms, ions, electrons has considerably increased during the last few decades. We are now able to manipulate a single atom, a single electron, a single ion to observe the light emitted by a single atom, and so on. This occurring completely new research fields like atomic interferometry, evaporative clocks, quantization, that allow us to ask new questions, to investigate new systems and new states of matter. One can reasonably hope, expect, that this will lead us to a better understanding of the world around us and to interesting new applications, which we cannot imagine now. And I think that is important of the basic research. First, hoping our vision of the world, that the progress of basic research, our vision of the world, every time we make a discovery, we change our vision of the world. For solving the right problem, energy, environment, health, that mankind has to face, I think this problem can be solved only by doing more science, not less science, contrary to what more and more people unfortunately believe. Attach bad picture to science, saying that science is to be evolution to ignorance. But that's not true. But good basic science can help mankind to solve this problem. And finally, I think that by scientific education, one can or ability, the ability of kids, children and students, to fight against ignorance, fundamentalism, which is a big danger of the 21st century, and to promote in this way the establishment of peace between nations, and make a connection with the foundation, peace foundation, which is a very important objective we have to all to take care of. So thank you very much for your attention.
Thank you very much, Professor Cohen-Tannoudji, for your very thought-provoking, yet very easy to understand lecture. May I now invite a few questions from the audience? If you're not sure how to phrase it in English, I'll try my best to translate it to English for Professor Cohen-Tannoudji to answer. Please.
In France, yes. After World War II, the state of research in France was catastrophic. All labs were empty, destroyed, the research was completely out. Fortunately, the few young people went out to the United States, Great Britain, and the PhD there, like Doppler, other people like Kastler, they came back and they started to build groups to make good teaching at high level. Amplification to all the different books of mechanics after doing the PhD project there. And they renovate completely. And I belong to fortunate generation, like who benefited from PhD work, who were able to learn outside, come back in the country and to make groups of people, to make schools of physics. And so physics has been very strong in the 60s, and they actually able to teach a lot of books have been written, a lot of programs on education and everything. So I would say that one of the best fields in France, around a few years ago. Unfortunately, during the last 3 to 5 years, the support for basic research has dramatically decreased because of budget. There are budget restrictions, and you know what political science wants to make it's easier to do it research. Because you are not trying to if you make something for science or for people, then you are trying to everybody can be to not to give back the money. So research is very fragile in this respect. And you know also the politicians always have a short term view, for maximum 4 years, the view of term of their method. Whereas basic research is the time scale 10 to 20 years. It takes 20 years for making a good book, so the situation is bad, and last year there has been a big revolution among the researchers. Most research directors of laboratories are designed, not designed to do research, but designed to get a scientific job, signing the bill, signing the paper, and that has finally perturbed the government, and which agreed to make $1 billion per more for the research. And I don't know if they will keep the command, but we hope that the situation will improve again. It's always necessary to fight, to explain to people what is important, why it is important to maintain a strong activity. If you stop that, it's very easy to destroy. You can make 20 years for building a group, and you can destroy it in 1 or 2 years. So, and then after it takes 20 years for restarting, so you have to be careful.
Congratulations for very beautiful and very interesting talk. I also heard something which I have never known before. But anyway, I would like to ask a few questions But for the first few questions, maybe on the basics principle, I guess when you're talking about quantum, everybody know that one of the puzzle is, and also very difficult to answer or understand is about uncertainty principle. When you take the atom down, then what would happen to the uncertainty principle? Is still be valid?
Can you define this word? What are the limits to the temperature and to look at the difference? You are perfectly right. We have delta X, delta T, and delta H bar. So the temperature delta T. If you want to take a T to zero, absolute zero, you have delta X. So obviously you cannot go to zero. Because then the sign of the experiment should be the universe. So when you put the numbers, you find that when you are at 1 nanometer, so 1 nanometer corresponds to delta E, so that the corresponding delta X, given by A over delta T, is a few microns, 30 microns. So to reach the nanocavity range, you must have wave packets which are 30 microns large. But 30 microns is still small compared to the experimental size. So we are not taking it like the of course, it is not violated in our present, but 30 micron is still much smaller than the size of our experiment. If we go to picokelvin or 10 minus 12 Kelvin or 10 minus 15 Kelvin, then we will start to have problems. But we are not taking this at this stage.
The second question is that actually the phase velocity of the atom of the light also becoming zero. The phase velocity of light also going to stop.
Oh, that the exciting experiment is a result, and where people use the light traveling through the medium of the common cells. But in this case, because they have very narrow line, the anomaly dispersion curves are extremely narrow, and the slope of the dispersion curve is very steep. And the group's velocity of light, which is determined by this slope, can be dramatically reduced. So this effect is just the effect of diffraction index. The diffraction index of the Brossel condensate near the level of atom can be so large that the group velocity reaches values that more than the fusion. And people have been able to see light propagated like moving back. But that's just an effect of diffraction index.
Now, one more question about application. Do you have any future for the co-fusion using this kind of technique?
I don't believe in co-fusion.
Probably not co-fusion, but fusion, because you can stop the atom.
I've described here the use of forces due to light to slow down. Of course, you can use the two directly. But there's a simpler way to experiment, to ionize them and to add them with heat. So until now, to my knowledge, these forces have not been used so much for accelerating, have been used to decelerate. And here's what they do. If you try to decelerate Chiang particle heat, electric field, you move the dissolution, you move the new value, but you don't change the expression. So people have not used these forces to heat them. But of course, the inertial fusion, you have a spherical target, and you have a very powerful to produce a shock wave to compress the microsphere and to reach temperature high enough to reach the fusion threshold. And that a lot of people are working on the world. So what is our one phase, we have in front right now, bigger tools, this is more things that people are trying to imitate fusion. But the different is important.
More questions? Notice that we have a few graduate students out there, so any questions from you guys?
example, you mentioned about the gravitational force of about 5 orders of magnitude, larger than the usual phenomena. Can we use any application from that, any benefit from that for the application or even for the fundamental study
Application of having the interaction
of the G? Can you repeat?
What application is the topic? The main application of this huge force. And so, of course, the behavior of the intended also because we don't need to do the power. If you really want the time, focus on the right element to the right attention. But there is no frequency which is very active when you really are one of the light active on a level. You can have a lot of things like communication, particular generation, select quantitative I think that's very negative.
Any more questions? Well, if there are no more questions, may I now invite the Associate Dean of the Faculty of Science, Associate Professor, Dr. Prof. to say a few words about this lecture.
Professor Claude Cohen-Tannoudji, Associate Professor Untitled Chapter, my graduate of Chiang University, Christian of the International Peace Foundation, academic colleagues, visiting guests, ladies and gentlemen. On behalf of the Faculty of Science, I express our sincere thanks and appreciation to Professor Tannoudji for his excellent lecture. As the President mentioned at the outset, the receipt of the Doppler laureate to our faculty has to be a prestigious occasion, and we are indebted not only to Professor Tannoudji, but also to the International Peace Foundation, which, whose important result for few weeks, BMW, Capricorn Bank, and Thai Airways International, for making today's event possible. Our 40th anniversary approaches. Today's special occasion can be considered to be only one part of those celebrations. Just as we have enjoyed the visit today, we hope that the professor and his wife, Madame Tannoudji, have enjoyed the visit to Chiang, even though it has only been a very brief one. Perhaps the travel will bring them back to Chiang again for a longer stay sometime in the future. And for now, on behalf of us all here in the Faculty of Science, our heartfelt appreciation for Professor Tannoudji for a fascinating insight into the role science and technology can play in today's society and in the world at large. It has been a pleasure and a privilege for us to host today's event, the first in the series of Nobel Science Laureate lecture. Thank you.
Thank you very much, Associate Dean. May now please invite the Vice President for International Relations of Chiang Mai University to present a small souvenir as a token of appreciation of Chiang Mai University for this lecture. Now, may I please also invite the Associate Dean of the Faculty of Science to present a small souvenir as well. you very much. Next, could I call upon all the distinguished guests, Professor Cohen-Tannoudji, to have a photo session together on stage, please? Finally, to bring this afternoon